Welcome to the Deep Dive. Today, we're taking a look under the hood at something we use constantly, but maybe don't think about too much: wireless networking.
That invisible stuff holding our digital lives together.
Exactly. And trust me, by the end of this, you'll see Wi-Fi in a whole new light. It's not boring tech specs. It's actually a pretty fascinating dance.
A very intricate dance, yes.
So our source material today is, interestingly, a set of practice questions and answers for the CWAP-405 wireless certification exam.
Right. Sounds dry, but hear us out.
It does, but what's great is these questions really nail down the absolute core concepts of how Wi-Fi works. They cut through the noise, like little nuggets of truth about your network.
They force you to focus on what really matters in the protocol.
Our mission, then, is to unpack these technical bits and turn them into real understanding for you. How does your phone even connect? How does it handle video calls? Is it secure? We'll cover all that. Think of it as your crash course in becoming genuinely clued in about the Wi-Fi all around us.
Okay, let's dive in. Where do we start? The very beginning, I suppose.
Yeah, let's do that. How do devices even find a network to join? What's that first step?
Okay, so fundamentally, it starts with something called the beacon frame.
A beacon, like a lighthouse.
Exactly like a lighthouse. Your Wi-Fi access point, your AP, is constantly sending these out, maybe every 100 milliseconds or so.
Okay.
And this beacon is basically the AP announcing itself. It says, hey, I'm here. This is my network name, the SSID.
Right, the name you see in your phone list.
Precisely. But it's more than just the name. It also includes crucial details like what Wi-Fi speeds it supports, the security settings it uses, information about the channel it's on. Basically, its capabilities.
So it's the AP putting its hand up saying, this is who I am and what I can do.
That's a good way to put it. It's laying out its offering for any device listening.
Okay, so the APs are broadcasting, but what about my laptop or phone? Does it just sit there waiting to hear a beacon it likes? Or does it, actively look?
Ah, good question. It does both, but it absolutely does actively look. That's where the probe request frame comes in.
Probe request, okay.
So your device, your client, sends out these probe requests. It can be specific, like it sends a request asking, is the My Home Wi-Fi network available? That's a directed probe.
Right.
Or it can send out a broadcast probe, basically shouting into the void, hello, any Wi-Fi networks out there I can talk to, and any APs that hear it will respond with a probe response, which is very similar to a beacon.
This is this back and forth, beacons announcing, probes asking. That's the initial hello of Wi-Fi.
That's the discovery dance, yes.
Yeah.
Absolutely fundamental to even getting online.
Right. But just getting connected, that's only step one. The really interesting stuff, for me anyway, is performance. You hit play on that Netflix stream, you jump on a Zoom call. How does Wi-Fi handle that kind of demanding traffic? And crucially, what makes it sometimes, well, not handle it?
Yeah, performance is key, and modern Wi-Fi has specific tricks up its sleeve. Two big ones from the 802.11 standard are WMM, which stands for Wi-Fi Multimedia, and RTS-CTS.
WMM sounds important. Quality.
Exactly. WM is all about quality of service, or QS. It lets the network prioritize different kinds of traffic. Think of it like having different lanes on a highway.
Okay.
So, voice calls and video streaming, they get put in the high priority lanes. Your email or a background file download, that goes in the best effort or background lanes. It ensures the time-sensitive stuff gets through smoothly.
Makes sense. So my video call doesn't get stuck behind a big software update.
Ideally, yes. And then there's RTS-CTS, request to send and clear to send. This one's more about managing who gets to talk, when to avoid interference and collisions.
Collisions, right. That sounds like it relates to that classic Wi-Fi headache, the hidden node problem. You mentioned devices maybe not hearing each other.
Precisely. The hidden node problem is a perfect example of why RTS-CTS can be so useful. Imagine you have two laptops, A and B, both connected to the same Wi-Fi router, the AP.
Okay.
But laptop A is too far away from laptop B to hear its signal directly, and vice versa. They're hidden from each other.
But they can both talk to the router.
Yes, exactly. They both have a connection to the AP. Now, what happens if both A and B try to send data to the AP at the exact same time?
Uh-oh. They can't hear each other, so they both think the coast is clear.
Bingo. They both transmit, their signals collide at the AP, and the data gets garbled, lost. Neither transmission gets through properly.
Nasty. So how does RTS-CTS fix that?
Well, before sending its actual data, the laptop sends a small RTS frame request to send to the AP. The AP then broadcasts a CTS frame clear to send, granting permission to that one laptop.
Ah, so the AP acts like an air traffic controller.
Essentially, yes. And since both hidden laptops can hear the AP, even if they can't hear each other, they'll both hear the CTS frame. The one it wasn't addressed to knows to wait its turn. It reserves the medium.
Clever. So it prevents those simultaneous unseen transmissions. That really shows it's not just about signal strength, is it? Coordination matters hugely.
Absolutely. Coordination and efficiency.
So if we want to know if our Wi-Fi is actually doing a good job, beyond just showing connection bars, what are the key things to measure? What really tells us about performance?
There are lots of metrics, but the two most fundamental ones are throughput and latency.
Throughput and latency.
Throughput is the big one people think about. It's the actual amount of data successfully delivered over a period of time. Not the theoretical maximum speed, but what you really get. Think bits per second, megabits per second.
Right, the actual speed you experience.
Exactly. And latency is the delay. It's the time it takes for a single packet of data to get from, say, your computer to a server and back again, usually measured in milliseconds.
And high latency is bad, like lag in games.
Precisely. High latency causes lag, makes video calls choppy, makes web browsing feel sluggish, even if your throughput is technically high. You need both good throughput and low latency for a good experience.
That makes total sense. Knowing those helps you figure out why things might feel slow. Okay, let's shift gears a bit. Performance is one thing, security is another. What's a major security mistake people absolutely need to avoid with Wi-Fi? A real no-go.
Oh, that's an easy one. Using WEP, Wired Equivalent Privacy.
WEP, I remember that, is old, right?
Ancient in tech terms, and completely, utterly broken. It should never be used today. Ever.
Why is it so bad? What's the flaw?
Well, it uses a static shared password, which isn't great to begin with, but the real killer was its weak implementation of something called initialization vectors, or IVs. They were meant to make the encryption stronger, but were implemented so poorly they were short and often reused that attackers figured out ways to collect them and mathematically derived the main WEP key very quickly.
Wow, so minutes, not days or weeks.
Minutes, yes. With the right tools, cracking WEP is trivial. It offers practically zero real security. You absolutely need to be using WPA2 or, better yet, WPA3.
Okay, message received loud and clear. No WP ever.
Yeah.
Good. Now, thinking about the physical side.
Yeah.
How do the signals actually, get around? So let's talk antennas.
Right, the physical layer. Well, the most common type you find on home routers and many APs is the omnidirectional antenna.
Omni, like all directions.
Pretty much.
Oh.
Think of it radiating signal outwards in a sort of donut shape, 360 degrees horizontally, but less signal directly above or below it. Great for covering a room or an open office floor.
Makes sense for general coverage.
Yeah.
Okay, and sticking with hardware and standards, Wi-Fi keeps evolving. Which big update really tackled the problem of handling lots and lots of devices talking at once? We have so many gadgets now.
That really came into its own with 802.11ax, which we commonly call Wi-Fi 6. It brought major improvements to a technology called MU-MIMO.
MU-MIMO.
Multi-user.
Yeah.
Multi-user, multiple input, multiple output. Now, MU-MIMO actually first appeared for downlink AP, talking to devices in the previous standard, 802.11ac or Wi-Fi 5. But Wi-Fi 6, 802.11ax, was a huge step because it made MU-MIMO work in both directions, downlink and uplink, so devices talking back to the AP simultaneously too.
So it's a two-way street now. Why is that so important?
It massively improves efficiency, especially in crowded places like airports, stadiums, or even just a modern home packed with smart devices. Instead of the AP talking to one device at a time, it can communicate with multiple devices in parallel during the same time slot. Less waiting, lower latency, better overall capacity.
That sounds like a really crucial upgrade for how we use Wi-Fi today. Essential, really.
It is. Along with other features in Wi-Fi 6 like OFDMA, it's designed for density and efficiency.
Okay, so we've covered connection, performance, security, physical stuff. Finally, let's get practical. If someone listening really wants to see what's going on under the surface to analyze their own network, what tools do professionals use to actually capture and look at these Wi-Fi frames?
Yeah, if you want to get your hands dirty, there are some fantastic tools. The classic go-to tool for general packet analysis is Wireshark.
Wireshark, I've heard of that. It's free, right?
It is. It's open source and incredibly powerful.
Right.
Now, to capture Wi-Fi frames specifically, you need a compatible wireless adapter that can be put into monitor mode. But once you have that, Wireshark lets you see everything: beacons, probes, data frames, control frames like RTS, CTS.
Yeah.
You can dissect the entire conversation.
Sounds like a deep dive tool for sure.
Yeah.
Any others? Maybe more Wi-Fi focused.
Definitely. For professional wireless work, tools like Air Magnet Analyzer Pro from Nettily are very popular. It's a commercial product, so not free, but its purpose-built for WLAN analysis. It offers very detailed frame decoding, expert analysis features, spectrum analysis integration. It's designed specifically for Wi-Fi troubleshooting and optimization.
So Wireshark for the deep dive, maybe Air Magnet for the pro toolkit. Got it. It's like being a Wi-Fi detective.
Pretty much. You're looking for clues in the invisible airwaves.
And speaking of detective work, when professionals are planning a new Wi-Fi deployment, they do something called a site survey. What's the main point of a passive site survey?
Right. A passive wireless site survey is all about listening. You walk around the area with the survey tool, maybe using software like Ikahow or Air Magnet Survey, but you're not actively connecting or sending data. You're just listening.
Just listening. For what?
You're listening for all the existing Wi-Fi signals. The main goal is to map out where the signal from existing APs reaches, measure the signal strength, RSSI, identify background noise levels, and crucially, see where different APs or networks might be overlapping or interfering with each other.
So you get a map of the existing wireless landscape before you start adding your own stuff.
Exactly. It gives you a baseline understanding of the RF environment. You find out where coverage is good, where it's bad, where interference might be a problem. It's absolutely vital for designing a network that will actually perform well. You need to know what you're working with.
Makes perfect sense. You need to map the territory. Understanding these tools and methods, it really feels like it demystifies Wi-Fi. So maybe a final thought for everyone listening. The next time you connect to Wi-Fi, just pause for a second. Picture that invisible dance. The beacons, the probes, the data flying back and forth, all managed by these intricate rules. And maybe ask yourself, what other complex invisible systems are working hard all around me, just waiting to be understood?